Any question before the class? I emailed you last Friday, I think, announcing second homework. This one. This homework is about writing assembly program, ARM assembly program, to sort this 32, the 32 data. Okay, this 8, 8, 8, 8. So 32. Okay, 32 data. So in smallest, so what? In ascending order, right? Smallest to the largest. So smallest number should be placed here, and the largest one should be placed here. Okay. So to do this homework, you need to know some more instructions. Last time we studied. Last time we studied until arithmetic instruction. Okay. So you need to understand. You need to know data processing instruction, memory access instructions, and branch instructions to do that homework. So today we will finish up this data processing, then branch instruction also, then basic, some basic memory access instructions. Okay, that would be enough. That would be enough for you to start the second homework. Okay, so today we will be moving a little bit fast. Okay, so last time we finished arithmetic instructions. Okay, so now let's jump into logical instructions. It is very mechanical process. Logical instruction is doing and, or, exclusive, or, those operations. A no-brainer, right? So you have and instruction. So look at this operation. You are taking this ALU as and gate essentially. It has 32 AND gate. Okay, 32 AND gate. So 32 of them, 32. So if we use the convention Rn and N, the convention, this one is taking LSB, Rn, LSB, right? N 0. Okay, so AND operation, AND gate, and the last one Rn 31, then N 31, MSP, right? So it is giving you the AND operation output. Okay, so it is bit by bit operation, bit by bit, right? Bit by bit, bitwise operation. Very simple operation. And OR operation, right? OR operation. This. So ALU you have OR gate, same, right? Similar, 32 OR gates, and exclusive OR gate. And this one is a little bit some special instruction, bit clear. Okay, we will talk about that. But it is essentially doing some AND operation, some inverted with inverted. Okay, so let's go over one by one. So this one, Madi, can you please read this one?
AND performs a logical AND between the two operands, placing the result in RD. It's useful for masking the bits.
Okay, so let me explain it this example. AND, right? You want to do AND operation of these two. So R0. So you have R0 register. Okay, 32-bit. Then 3. 3 is what? In binary, all zeros. Then the last 2-bit is 1. So if you do AND operation, you are essentially doing what? You are taking out that, that 2-bit. Whatever it is, you are taking out this 2-bit. That is output. Okay. And the rest 30-bit, upper 30-bit are 0, right? So you are taking out that 2-bit with AND operation. Simple operation, right? And this one, Hojun, can you please?
EOR performs a logical exclusive OR between the two operands, placing the results in the destination register. It is useful for inverting certain bits.
Okay, thanks. EOR operation, exclusive OR operation, that is very useful. There are two purposes, two usages. The first one, you can use that. You can write this code EOR R0 R0 R0. So what is the output? You are doing XOR operation and place into R0. What do you think? What is the output? R0 will be what? R0 will be 0, all 0. So it is very useful to initialize this destination register to 0. Why is that? Think about this XOR operation, truth table. A, B, and Y. Okay, A, B, Y. Truth table. You list all possible input cases, right? 2 bits. So 4 cases. 0, 0, 1, 1, 0, 1, 0, 1. So output is what? 0, 1, 1, 0. Okay. So you are doing XOR operation of 2 same operand, meaning this case, right? This case and that case. Right? So you are providing same, either 0, 0 or 1, 1. So output will be 0. So XOR operation is very useful when you want to initialize this destination register to 0. Very cheap way to initialize destination to 0. And that example, okay, look at this example. That example, second operand is 1, right? Meaning this case, second operand, think of it as a second operand A. Okay, second operand is 1. Okay, you are doing R0. Okay, and the last one is 1, 1. So you are doing XOR operation 3, EOR operation. Okay, so then if you look at this truth table, 0, right? If you supply 0, then no change, right? No change, right? So that information, okay, no change. Okay, but if you supply 1, okay, so you supply 1, then 0 to 1, 1 to 0. So you are essentially inverting that B2. You are inverting, these 2 bits. Okay, so that is useful. So first, 2 purposes. First one, to initialize this destination register to 0. And second purpose, you can invert this first operand if you supply 1. Okay. Okay, so let's go through some example. This one is very simple. So OR operation, right? OR operation. You are doing OR operation of R1 register, which is this one, and R2, this one. So what is the output? R0. Simple, right? So 1, 2, 3, 4, 5, 6, 7, 8. And this one is very special instruction, bit clear. So the purpose is first operand, right? R1, this one, 4 ones. Okay. For simplicity, I don't want to write 32 binary number. Okay, so only 4-bit binary for simplicity. Okay, R2 is this number. So what is the purpose? Bit clear. You want to clear some bits in first operand, some bits. You want to clear some bits in some specific bit positions. Those bit positions are specified in second operand. In this case, okay, so R2, right? Bit position, first bit position and third bit position. Please clear the bit, first bit in first operand and third bit in first operand. So result will be this one. Bit clear. Okay. So if you go back to that slide, essentially you are doing this. Okay. Think about this. You are inverting second operand. Okay. CPU ALU will invert second operand and do AND operation. So look at this example. So you invert, okay, you invert second operand, then do AND operation with R1. Okay, then you get this one. Okay, so interpretation is, so how to interpret? Interpretation is you want to clear some bits in some specific bit positions. Those bit positions are specified in second operand. Okay, so you want to clear first bit and third bit in first source operand. That is interpretation. Okay, bit clear. Which bit you want to clear? The first bit, third bit in first operand. Which bit you want to clear? Bit clear, right? Bit clear instruction. Okay. Any questions so far? Yes, Suho. Okay, Suho. Yeah, good point. Okay, instead of using this, you can use yes. ARM case. You can use move instruction R0. This one. Same operation. Okay, so you can initialize R0 with 0. Same operation. Yes. Correct. So yes. Any question so far? Okay, let's move on. Comparison instruction. I think that instruction will be used a lot because in high level language we are using conditional statement a lot. If statement, okay, and while statement, some condition, right? As long as this condition is satisfied, you keep executing this code. Otherwise, you exit, right? While for 0 to this one plus, right? So condition is met. As long as condition is met, you keep looping. Otherwise, you exit. Condition check, right? Case. So in high level language, you use this conditional statement a lot, right? So to check this condition, you want to compare these two. Okay. So for that purpose, you can use compare instructions. Okay, this one. Camden, can you please?
What do you want me to do? Read the slide?
Oh, yes, these two bullets.
Right. The comparison instructions update the CPSR flags according to the result, but do not affect other registers. After the bits have been set, the information can be used to change program flow by using conditional execution.
Okay, thanks. There are 4 instructions in ARM Cortex A9. Compare instruction. Okay, compare negated and TQ and TST. Let's go through one by one. Okay, for next slide. First, compare instruction. So that is example of compare instruction. You want to compare these two, right? So for example, in this case, assume that A is placed in R0, B is R1. Okay, you want to compare these two. Then you can use R0 and R1. Okay, like this. Okay. So if you write this code, compare, then CPU will do what? What do you think? Internally, CPU read this instruction and decode and execute it, right? In ALU, okay, CPU will do subtraction, right? The subtraction, R0 minus R1. Compare, right? Subtraction. Then this one is a first source operand, right? Source 1 and source 2. Then there is no destination. no destination register. Okay, it is just doing subtraction and update flags, NGCV flags, right? ALU is generating NGCV and update CPSR registers, right? NGCV, those flags, negative, 0, carry out, and carry and overflow. Okay, so based on that, okay, next instruction, so next instruction can use these updated flags to do something, okay, to do some operation. Okay, so again, the purpose of that instruction is updating those flags. That's it. That's it, right? No destination register. Okay, CMP instruction, just compare, right? So doing subtraction. CMN instruction, CMN, compare negative, meaning CMN. So CMN, R0, R1. So you are comparing R0 against a negated negative R1, meaning you want to compare R0 and minus R1, okay, negative. So that means internally CPU will do subtraction. So R0 minus this minus R1. So you are doing, CPU will do addition, right? Addition operation. Okay. CMN instruction, compare negative. Okay. So you create negative number of R1 and compare with R0. So R0 minus negative number of R1. So you are doing addition, right? CPU will do addition. So again, no destination register. The purpose of the instruction is updating those flags, NGCV. Okay. TST instruction, test. That instruction is doing logical operation, AND operation. Okay. CMN, CMP, CPU will do subtraction. Okay. And TST instruction, CPU will do AND operation. Okay. AND, bit by bit, AND operation. Then update flags except V, NGC flags, NGC flags. Okay. TEQ instruction is doing also logical operation, exclusive OR operation. Then update those flags, NGC. Okay, NGC flags. So let's go through example. This one. Okay. CPSR initially, before you execute this code, assume that initially NGCV are all 0. Small letters, right? NGCV, meaning all zeros, right? 0, 0, 0, 0. And R0 has 4, R9 has 4. So compare. Then what do you expect? No destination register. We are interested in NGCV. Which flags? 4 minus 4, right? So 0 flag for sure, right? So you have NGCV flags, right? And 4 minus 4. So result is 0. So 0 flag will be 1. Okay. How about other flags? N flag will be what? 0. So MSB, most significant bit of that, output, ALU output is 0, right? All 0. So MSB is 0. So that will be 0. How about carry flag? Carry flag will be 1. Why is that? Why is that? Because computer is doing 2's complement. Computer is using 2's complement data for negative number. Again, so let me go through one more time. 4, that operation will be done here with addition. Then 4 plus minus 4, right? So minus 4, how to create minus 4? 2's complement notation, right? So invert, then add 1. So computer will do, ALU will do that operation. Okay. So how to create 4? Invert, then let me write hex number, right? So 4, 7 zeros and 4. Okay, this 4. Okay, this one, same 4. Then you have to invert. That means 7 F's, right? This one. Or 4 zeros. So invert 1, 1, 1, 1. That is F. Okay, in hex. So F. What is that? 4 is what? 0, 1, 0, 0. Binary, right? Invert. Flip all the bits. So 1, 0, 1, 1. So that is 8, 2, 10, right? 10 and 11. This one plus 1. 11 is what? B, right? B. Then you have to add 1. So C. C. Okay. And do addition. Okay. So this, that is this one. Okay. So 4 plus C. So C is a 12, right? In decimal, 12. 12 plus 4. 16. So 0 in hex, right? So carry out. So 1 plus F, 0. You have carry out 0, 0. Keep doing this, right? 0, 0, 0, 0. Then finally carry out will be 1. Okay, that is why carry bit is set to 1. Okay, and overflow. Overflow is what? Last carry out and second last carry out. That is exclusive operation. So last carry out and second last carry out, right? 1 and 1, 1 and 1. Okay, 1 XOR 1. So according to the truth table of exclusive OR gate, 1 and 1, then there is 0. There is 0. Right? So 0 flag will be set to 1, 0 and carry flags will be set to 1. Okay. So run that code in Vitis IDE, right? So initialize R0 to 4, R9 to 4, then run this code on Zboard. So you can check out, flags. 정훈, compare. Okay, good question. CMP, CMN at S, TST. Yes. The question is, you are correct, 정훈. John's question is SUB. So let me write down. Okay, 2 instructions. Compare, right? Compare. You want to compare R0, R1. Okay. Then CPU will do internally will do subtraction operation, right? And update that operation. Update update NGCB. Okay, that is the purpose. Okay, compare, update NGCB. If you write subtraction instruction SUB, let's say R2, R0, R1. So you are doing subtraction of these two, then result will be saved here. So subtraction instruction, but if you have S suffix here, case, okay, S, that means the base instruction, then operation is R2, R0 minus R1. In this case, you have destination register. Here, no destination register, right? So you are going to, CPU will update R2 register like this. And if you have S suffix, S, meaning after subtraction, update NGCB as well. So second operation, if you have S, update NGCB. Okay, NGCB. Two operation. So so difference between these two. No, here, this one is the one. Okay. Any other questions? How and we can make okay. Yes. That is Juan. That is excellent, super excellent question. What do you think? And or operation, how to make carry? Yes, excellent question. Actually, I don't want to talk about that because that is taking time. Okay, but Juhan raised that question. So it says, look at this, TST, right? It is doing AND operation, then update, NG, negative. So it's okay, right? Negative and negative and zero flag, right? Your ALU is doing this. ALU is doing AND operation, right? AND. Okay, taking two source operand, Rn and N, then output, right? And bit by bit operation, right? Bit by bit. So Rn and N. Okay, so bit by bit. Okay, so first bit and doing AND operation, then output, right? Second bit, AND operation, output, okay, and so on, right? The last one and AND operation. Then what do you mean by, so a negative flag, right? Negative flag is set based on this MSB N bit, right? Okay, N bit will be set, and zero flag will be set based on that outcome, whole output, whole outcome. Right? Zero, then zero flag will be set to 1. And the carry. So what do you mean by carry? You are doing bit by bit operation. There is carry out. There is carry out. No carry out, right? Bit by bit operation, right? No carry out. Then how do you set carry? Okay, that is a question, right? So carry. So if you go back, logical instruction. Where is that logical? Probably move instruction. Okay, here. So in case of move instruction, Juan, I think same thing applies to move instruction, right? You are just moving, right? Same thing. And how to set carry, right? Negative, zero flags. Setting those flags are making sense. But carry, right? Just moving, right? So how to, is it generating carry out? Move instruction? So look at this. Carry is a set from barrel shifter output. That is, small, nasty, small detail. Okay, I don't want to discuss actually in Arm. Okay, nasty, small detail. But most of the cases, you don't have to worry about that, C, carry, set in move instruction and logical instruction. But Juan is curious about that. So carry is set from barrel shifter. Look at this. Okay, here, barrel shifter. Okay, barrel shifter. So second operand, remember? Second operand, you prepare second operand, right? And using this barrel shifter, right? Using this barrel shifter, you are preparing this big N. Okay, second source operand. And in case of move instruction and logical instruction, okay, look at this. Move instruction. If you look at the instruction encoding, you can specify this variety. You have this variety of options you can use in move, right? So the register you read from register file goes through shifter. Okay, that shifter output is used to set carry flag. Okay, here. Okay, move instruction. Same thing goes to logical instructions. This one. So in this case, a simple, case, right? Simple assembly code, but you can write this code. And R0, R0, probably R1. I want to do arithmetic shift right by 3-bit. That is second source operand. Right? First source operand, second source operand. So you are using shifter to cook up this big N. That is Rn. First source, second source. So carry, right? Carry flag will be set if you put S. If you put S. Carry flag will be set based on that output, shifter output. Okay? So, I updated. I don't know if you are using this updated PowerPoint or not. If you check out this, backup slide here. So, flag update varies depending on data processing instructions. So here I wrote, right? Nasty small detail in ARM instructions. Okay. So most of the cases you can intuitively, most of the cases like this. So that is probably you want to implement in assembly. Okay. So signed integer. Okay. You want to write this conditional statement in high level language. How to write this conditional statement in assembly? Just compare instruction. Compare instruction is updating all of the flags NGCV. Compare, right? So in most of the cases, right, if you are dealing with integers and use compare, then you don't have to worry about which flags are set. All the flags will be set. Okay, don't worry too much about that. So arithmetic instruction will update those flags, but there are some exceptions. Okay, and logical instructions update NGC, but V is not changed. Okay, and also carry is set based on barrel shifter output. So go to here. So some example. This one is from ARM architectural reference manual. This one. This one. ARM architectural reference manual. So let me show you one thing. Some examples. Okay. So because it is nasty small detail, if I bring up this issue, then some of you are confused. Okay, it is very complicated. I don't want to write assembly program. That is why I didn't bring up that issue. Okay. So if you know enough about ARM instruction and programming, then you can go back to this architectural reference manual to check out the details probably. So addition instruction, for example. So ARM addition instruction, and that is explaining detailed operation of this addition instruction. Right? If you scroll it down, look at this. NGCB, those flags are updated. Okay, and then check out some logical instructions like AND. Okay, so AND instruction. Scroll it down. ARM encoding A1 ARM sum encoding. Scroll it down. Look at this. NGC V no change. C, how about C? C carry. What do you mean by carry? Carry. If you scroll it up. So that is explaining this carry. So you have to search what is this function. So pseudocode okay. So search. Okay, I think go back to some. Okay, this one. Okay, so that function, okay, this function. So, you know, look at this. It is, you don't want to read this pseudo code, right? So, you know, carry out, return this carry out. Carry out is generated from shifter. So, you know, again, you know, a nasty small detail. Okay, I don't want to raise, right? But, you know, good news is most of the cases you don't have to worry about this issue. So, so here, okay, here, move instruction, right? Carry. What do you mean by this carry? Move instruction, is it generating carry out? So what do you mean by why? Why is generating carry out, right? Just move, right? So that is, you know, that is updated based on that, you know, pseudocode, right? This one. What does that mean? The shift underscore C. Next one. So, you know, I copy and paste it. Some important pseudocode from the datasheet. But again, you don't want to read this detail for now, right? For now. Okay. So if you are familiar, you know, enough with ARM programming, probably you can go back to this issue. Juan, is it answering your question? Yeah, thanks for raising this issue, but you know, again, nasty detail. Okay. So that is okay. That is about logical instructions. Okay. So now let's move to branch instructions. Okay. So we are going to study only two instructions. Branch. Very simple. Okay. This one. Suho, can you please?
Branch instruction changes the flow of execution or is used to call a function. This type of instructions allows programs to have subroutines, if then else structures and loops.
Okay, thanks. Two instruction, branch, and second instruction, branch with link. Very simple. Okay, this one. Okay, Hojun, can you please read? Let's read this and let me explain.
Branch and branch with link are used for conditional or unconditional branch. BL is used for the subroutine call. To return from a subroutine, use move PCR14. Branch target address. Sign extends the 24 bits signed immediate to 30 bits. Left shifts the results by 2 bits. Add it to the current PC, actually PC plus 8. Thus, the branch target could be plus minus 32 megabytes away from the current instruction.
Okay, pretty complicated, you know, explanation, right? So don't worry too much about that. Let me explain about this. But before that, take a look at this instruction format, branch instruction format. Okay, B, branch and link. Look at this L. If you use B instruction, then this field 24 bit, that will be 0. Okay, so BL, branch with the link, then that bit will be 1. So CPU can differentiate. Okay, is it branch instruction or BL instruction by looking at this 24 bit. Okay, let me show you example first. Okay, branch instruction. Program will be executed from the top to the bottom. Okay, that downwards. Okay, so CPU hit branch instruction, branch forward. This label. Okay, then CPU will skip these 3 addition instructions and then execute subtraction. Okay, branch forward, right? Branch. Okay, branch it to this location. So skip those 3. So these 3 instructions will never be executed because you always branch. Okay, so it is a useless code, right? Second example. So from top to the bottom, right? Execution flow. If CPU hit branch instruction, branch backward. Okay, so program counter will be set to that location. So branch to this addition. Okay, then addition, subtraction, addition, hit, same branch instruction. Then you have to go back. Keep looping forever. Endless loop. Okay, endless loop. Okay, branch backwards. So this one is an example of branch with a link instruction. Branch with the link. That instruction is used to make a function call. Function call. Okay. So from the main, you are calling some function called foo. Okay. From main to function, right? So branch instruction. So b, if you do b foo, for example, foo. Okay, b. Then that instruction. So bl foo. So what is the difference between two? That instruction, let's say foo is function, some subroutine. Okay, whatever it is. A branch, that instruction will set program counter to foo. Okay, foo, the name, right? This name or label. What is the meaning? What is the meaning of this function name? The location of first instruction. Okay, first, whatever you have here. So addition instruction, something. The location of the first instruction. That is function name, right? Label. Location of the first instruction in that function, right? So the location or address, location of the first instruction in that function, right? Function location, right? So that is the operation. This one is doing the similar operation. Program counter will be set to this location. And then one more thing. Second, the return location. So after making a function call and execute it, then you have to return back to the next line. Okay. So let's say it is the position of next code. Let's say you have addition. Okay. So that position. Okay. That position. The location. That position will be saved in link register, which is R14. Hardware, right? Hardware will do these two, CPU will do these two operations. If you execute BL, branch and link, branch with a link, right? You are making a function call, you need to store the return location, right? That is too obvious. Return location is saved in link register. Okay. So when you return back from a function, okay. So making a function call, then execute the foo, then at the end, you have to return back to this place, okay, and execute the addition. So at the end, before you exit, before you return, you have to use move, because you saved return location in LR, actually CPU, right? Hardware saved return location in LR. You have to use that instruction. LR to PC. Return location to program counter. So that PC, so that CPU fetch next instruction. Okay. 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 Is it programmer step to brand backup old R14? Oh yes. So Haechang, yeah, great question. Haechang is probably talking about nested function call, right? What if inside, right? Inside foo, what if you call another function? So inside here, you are calling some function, right? Some function called foo2. Okay. then here you are using BL, right? BL foo2. That means branch with a link. That means LR register. Right? These two operations will be done, right? In hardware. First one, program counter will be updated with foo2, the location of first instruction in foo2. Second, link register will be the return location, this one. Okay, let's say this one, this position. Link register will be overwritten. Here, you updated here, but link register will be overwritten. So before you make a function call here, you have to make sure you backup here, backup link register to memory. Actually, to the stack. You have to backup link register to memory, right? In stack area. We'll talk about that. Okay. So link register is used a lot, right? Whenever you make a function call, right? Especially nested function call, right? Here saved, here you are overwriting link register. Right? Yeah, good question. Thanks. So you have to do everything yourself, right? In C language, high-level language, compiler will do the job. Compiler will back up, right? Because you are making function call in a nested manner, nested fashion, right? So compiler will figure out, okay, I have to back up link register, right? So that will make your life easier. But if you write assembly program, you have to do everything yourself. In that way, you have better understanding of computer, right? Computer is doing stack operation, some details, right? So you can have better understanding. Okay, let's go back to this place. Okay, now, it is very simple. Usage is very simple. Branch with a link, right? Usage is very simple, super simple. But I want to talk a little bit more about that instruction, this part. Okay, so if you look at this, branch destination, that is the destination, foo, right? That is the destination, right? Branch, let's say this label L1, right? This L1 is located here, L1. So the question is how far you can branch, how far you can branch, okay? That information, how far, that information is encoded in lower 24-bit in ARM, okay? How far? And ARM architect decided to put a number of instructions here. So from here to here, okay, how many instructions are there? Let me give you a specific example. You have sub, LDR, let's say you have STR, okay? So you have 1, 2, 3, 1, 2, 3, 4. 4 instructions away, right? 4 instructions away from this branch, okay? So 4 will be encoded in that 24-bit field, 4. So here, again, number of instructions between branch and the destination. Okay, but that is not actually 100% true. Okay, so before that, so you can branch forward. Sometimes you can branch backwards. The destination is located backward location, right? Backward. So plus forward, right? And backward. Okay, so plus position and minus position, right? Forward, backward. So computer will use, look at this, signed, right? That is why signed immediate 24-bit. signed, right? Signed number. Okay. That is one thing. One more thing is, I told you, right? I told you in branch instruction in lower 24-bit. So you are encoding number of instructions between branch and the destination. Okay, but that is not 100% true. In to be more precise, ARM architect decided to use PC plus 8 position. It is a little bit confusing. So this one, current location. Program counter is pointing this one. Okay, I want to read this one and CPU execute branch. And this one, if you use it as as base, then PC plus 4 position. Next instruction is located PC plus 4 location. Okay, this one PC plus 8 location. And ARM architect decided to encode number of instructions from here to destination. So here 1, 2 instructions away. So in this specific example, 2 will be encoded 1, 2 instructions away. 2 will be encoded in here. You will be if you are interested in ARM, probably take a look at this ARM architectural reference manual. This one, this reference manual. Then you will see that terminology a lot. PC plus 8. PC plus 8. And why do you think so? Why do you think ARM architect decided to use that information? Okay, that information. So why do you think so? It sounds very strange, right? PC plus 4 branches useless. What do you mean by that, Hojun? PC plus 4 branches useless. So what do you mean? What do you mean by that? Branch for PC plus 4. Branch to here means nothing. Branch to this position. But you can write this code, right? Anyway, you are the boss, right? You can write this code. Destination is this location L1. It looks very strange. Okay, you are branching, but you can write this code. It is illegal. It's not illegal. It's a legal code, right? Okay, code, right? You are branching to here. Anyway, right? Compiler will generate, code, machine code. Any other thought? So you have to think about the pipelining in CPU, right? Last semester we studied a 5-stage pipeline, right? Think about a 5-stage pipeline. Branch instruction, right? B to I need some more. Okay. BL1. Okay, this instruction. BL1. Then if we assume 5-stage pipeline in Cortex A9, then fetch, decoding, execution, memory access, write back. Okay. Then branch instruction is done. The next instruction, addition, fetch, decoding, execution, mem, write back. Then subtraction, right? Fetch, decoding, execution, memory access, write back stage. That is clock, right? Clock is running like this. CPU clock, right? For example, the clock speed 2 gigahertz. Okay, 2 gigahertz clock time, right? So take a look at these pipeline stages. You are reading fetch stage. CPU just read, right? CPU just read that instruction branch. In decoding stage, you are interpreting this branch instruction. CPU will interpret. Okay, so what do you have to do? Okay, I have to do branch, right? CPU will figure that out by looking at operation code. That operation code 101. Okay, by looking at this, okay, I need to do branch. I need to update. Actually, I need to update, right? PC will be updated, right? L1. Then execution stage, CPU will ALU, right? ALU will compute branch destination location, right? Destination location, destination. So it is a relative addressing, right? From that position to that location, relative location. So to compute that relative location, so you have to use ALU. Then you need program counter information. But look at this, program counter location. This one addition PC plus 4 position, and subtraction PC plus 8 position, right? So you are patching. Program counter is PC, right? PC plus 4. This one, PC plus 8. So when you compute branch destination in execution stage, this time, program counter is already updated to PC plus 8. Already hardware, right? So instead of using this original PC, to use this PC, you have to pass and pass, right? That means you need flip-flops to pass that information. That is, hardware resources. So you don't want to use those hardware resources. Instead, you want to use just updated program counter. So ARM architect decided just to use this updated PC plus 8. Updated information. So that is why, PC. Okay? PC plus 8. Then how do you compute? Inside the CPU, internally, inside the CPU, how CPU compute branch destination, this location. So starting from PC plus 8, okay, PC plus 8, that information is available, okay, to ALU addition, right? That information is supplied to ALU adder, okay. Second operand. So you have information, relative position, okay. How far from that location? That is encoded here, number of instructions. And each instruction is 4 byte in size, right? ARM instruction, 4 byte. 4 byte in size, ARM instruction, right? So you have to multiply this number by 4. Okay. So number of instruction, you are taking out number of instruction, shift left by 2 bit. That is has the same effect of multiplying this one by 4. And also one more thing you have to be careful. You can branch forward or backward. So this is signed number, right? Signed. That means you have to do sign extension. Some sign extension here. Sign extension. Hardware will do that operation. So that is a description. Sign extend is 24-bit. I'm talking about hardware will do this operation, CPU. Right? Sign extend is 24-bit. Okay, to 30-bit. Okay, take out that guy, take out this guy, this information, and sign extend it to 30-bit. Then shift left by 2 bit. The reason is because instruction. It is encoding number of instructions, and each instruction is 4 byte in size. So you are doing shift, 2-bit shift. Then add PC plus 8. Then add that information with PC plus 8. That is branch destination. So I'm trying to explain the story behind this encoding and this PC plus 8 and hardware operation. So in that way, you get better understanding of branch instructions. Okay, so let me give you one example with Eclipse. Okay, here side by side. Let me use branch. Any instruction is okay, right? BL1. So what if I write destination is located here? What do you think? Like this. Then what do you think? This offset, sign immediate. What information do you expect? In machine code. Okay. Before showing you the machine code, compiled machine code, what do you think? So PC, right? PC plus 4 and PC plus 8. Yes, Minsong, yes, 0. That is correct, right? 0. So that information it contains, it will be 0, right? Let me show you. Main. Look at this. Branch and instruction encoding, machine code. So row 24-bit, all zeros. 6 zeros in hex, right? So that is one. What is A? A is in binary 1010. A, right? 101, L is 0. So 0. What is E? E means this condition field. If you remember E, A always, right? AL, right? AL condition. So remember this one. This one, AL. AL is E. E as in Edward, right? E. 1110. Okay. So EA, that is machine code. Okay. So one more. Okay. Branch. Okay. So one more example. Okay. So what if I write? What if I set destination to? Probably easy, right? This location. So 24-bit. 4-bit will be what? So PC plus 4 location, PC plus 8, counting from here, right? So location, destination is 1 instruction away. 1 instruction away. So you will have 1. Okay, compare it. Okay, then search with 1. Okay. Okay. So one last example. What if you set branch to okay, I don't know. Let me cook up here like this. Okay, what if you write this code? Compare it. What do you think? What do you expect? For readability, let me write this. Confusing, right? So negative location from here, negative, okay? But you have to count not from here, but PC plus 4, PC plus 8, counting from here. So -1, -2, minus 3 instructions away. Right? Count from here. 1, 2, 3. So minus 3. What is minus 3? Minus 3. Computer is using 2's complement number system, right? So start minus 3, starting from this one, right? 2's complement. So in hex, we are talking about 24 bit, right? 0, 0, 0, 0, 0, 3. Okay, let me 0, 0. So 4, 6, 4, 2. So 6, right? 24 bit. So flip all the bits, right? F, F, okay, F, 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 what? 0, 0, 1, 1. So flip all the bits, right? 1, 1, 0, 0. So 1, 1, 0, 0. What is that? 12, right? So C plus 1, T. Okay, C plus 1, right? So their information will be this one. So let me show you the code. Okay, did I compile it? I don't know. Yes, okay. So check out this. Look at this, right? 5 Fs, and T. Okay, so that is minus 3. So CPU, right? CPU again, internally, right? When CPU compute the destination, CPU will do sign extension, right? Sign is 1, right? 1, 1, 1, 1, F, right? Sign is 1. So sign extend, right? Okay. That means you have FF, right? FF, 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 T. Okay. Sign extend, then to be shift left. Okay. To be shift left. Okay. Then PC plus 8. Right? PC plus 8 addition. Okay. That is done by hardware internally. Okay, any question about this? Branch? So I'm trying to not only explain the function, but the story behind that instruction encoding, right? So that is helping you a lot actually. By looking at this, you can figure out what you can do or what you cannot, right? You can jump, you can branch very far away, very far away. Right? Destination can be super far away. How far? 32 megabyte away. Positive or negative. Okay, because we have 24 bit, right? And it is encoding number of instructions. That means to be shift, then you can think of it as a 26 bit, right? But positive, right? Positive, negative. So you can use 25 bit each for positive, negative, right? 25 bit to the power of 25, which is 32 megabyte roughly, because we are counting from PC plus 8 position, counting from, right? 32 megabyte away. Okay. Okay, let's move on to memory access instructions. Okay. This one is very simple. Okay, this one, 성목, can you please?
To store memory access instruction transfer data between memory and CPU register. Single register transfer, multiple register transfer, swap instruction.
Okay, are you in Starbucks?
Yes, sorry.
Huh? Where are you? Starbucks or? Okay. Okay, so memory access instructions. ARM is providing several memory access instructions, but today we'll talk about single register transfer. Okay. On Thursday we'll talk about these two. So simple memory instruction first. ARM is providing LDR memory read, okay, memory write store, and this one is byte read. So LDR instruction is reading 4 byte. Okay, we have CPU, which is 32-bit architecture. 32-bit architecture. What is the meaning of 32-bit architecture? Data path. Data path is based on 32-bit, right? ALU. So it is taking two 32-bit data and generate 32-bit output and register file, right? RF. That is 32-bit, right? Each register is 32-bit in size. So the reason why it is 32-bit, because 32-bit architecture, you want to provide 32-bit to ALU, right? Everything is based on 32-bit. Okay, so memory to read 4 byte data, which is 1 word, right? This is a word, 1 word, 1 word, 1 word, right? To read 1 word, you can use to read 1 word and place into some register, you can use LDR. Okay, LDR. And to write 1 word to memory, you can use STR, 4 byte. 4 byte data. Okay. And sometimes you want to read 1 byte, not full 4 byte. Sometimes you want to read this 1 byte. Okay, 1 byte and place into some register. Okay. For that, you can use either LDR load byte, or you can use LDR signed byte SB. Here, that byte. LDR SB. So why do you need 2 instructions? 2 instructions for byte read. It is very obvious, right? Why is that? Reading 1 byte and placing into 4 byte. You see some problem, right? 1 byte, 4 byte, size mismatch. Size mismatch, right? 1 byte data. So in this case, LDR case, right? LDR case, you don't have any problem. You are reading 4 byte and destination is 4 byte. No problem, size equal. But you are reading 1 byte here. And you want to place that byte into 4 byte register, which is 4 byte. Size mismatch. Then what do you have to do, right? Hardware will place that information. Let me write specific data. Let's say you have FF, okay? FF, the data, and place into R5 register, for example, okay? Then FF will be placed. Let me write R5, okay? R5 register, LSB, SP. That data will be placed in LS byte position. Okay, LS byte position. If you use LDRB or LDRSB, okay, that information will be placed here. Then what the question is, what do you have to do with upper 24-bit? In case of LDRB, okay, this one is signed, right? Signed byte. LDRB, you are filling, CPU will fill this 24-bit with all zeros. Zero extension. This one will do zero extension. Zero extension, right? 1 byte read, but that will be, you need to cook up 32-bit, 4 byte. You need to expand, right? But when it comes to SB, signed byte read, that will be filled with MSB of this data. Most significant bit. So the result will be F, everything is F. Okay, in this case. So it depends on your interpretation of this data, your data interpretation. If you think this data, okay, I think that I'm going to consider this data as unsigned byte. Okay, I'm going to think of it as unsigned byte. Unsigned meaning 0 or positive, right? No negative. Then when you read, you have to use LDRP. Okay, what is this number in decimal? If you think of it as unsigned byte, 255 positive. What is the number? Okay. That is still 255 positive. But if you think this number as signed byte, what is the number? The number is -1, right? -1, according to 2's complement notation, right? Then you have to use LDRSB. What is the number? All F's. That is still -1. Same number. So data, right? Data, it depends on your interpretation. Data, right? Same data, but the meaning of this data is different depending on your interpretation. So in this case, I consider this as integer, right? Byte, signed integer or unsigned integer, but it doesn't have to be, integer. It can be part of MP3, music, file. HWP, part of HWP, file, right? It could be, right? So it depends. The interpretation of data depends on you, programmer, right? Programmer. Okay. So depending on your interpretation, you can use different instructions. The same thing goes to half word read. LDRH, LDRSH. Half word means 2 byte. 2 byte read. You read 2 byte and place into 4 byte register. So we have some problem. Size mismatch. Right? So depending on your interpretation, if you think 2 byte, these 2 byte as unsigned number, then use LDRH. So the CPU do 0 extension. If you think of it as signed 2 byte, then you have to use LDRSH. Then CPU will do sign extension in hardware. So the meaning of this data does not change. Okay? After extension. Okay, I think we have to stop here. Any question before closing up? I think that would be enough information, but for you guys to do second assignment, try to interpret, try to analyze this example code. It is very simple. Example code, the one you put in this the code you put when you set up this environment, right? So it is using LDR, SDR to copy this data. Okay, copy this data to this destination, source and destination. You are reserving 16 word, 16, okay, space, reserving 16 words in this location, from this location. And this code simply loop, right? Loop. Simply copying 1, 2 here, 2, 2 here, 3, 2 here, and so on. Try to interpret that example code. That will help you, I think. Okay, I guess that's it for today. See you on Thursday. Bye. Okay, thanks. Thanks.